So I'm going to move on to the overview lecture. So my current plan is to, so measurement error is a kind of important topic, and also random effect model or mixture model. They are all, specific topics. So that may need some introduction, especially the high level introduction, may be helpful to you guys. And so I'm gonna kind of make 30-minute overview lecture and record it and upload it to the Canvas so that you guys can watch it before the class so that I can move on faster and focus more on the details in the class. So that is the idea. But to give you a sense of what the overview lecture is, this is my style. So by the way, I'm gonna okay. So everybody in stat department should know Bayes' theorem, right? I mean, it's not really surprising or new. Even 101, stat 101, we learn Bayes' theorem. But I personally, I realized the value of Bayes' theorem much later stage of my career. Then, so when I was a student, I don't know. I just learned how to solve Bayes' theorem, use the Bayes' theorem to solve the problem, but not really understand the true meaning. And here's and now I think that it's really important, and I hope that you guys can agree with me. And so let's use COVID example. Okay. So C is a true status. This is a status, right? So 1 or 0. So I'm going to use, by the way, I'm going to use red color to denote missing or unobserved or unknown. Okay. You never really observe true status of your disease, right? You never know. You only know by using the test, whatever the PCR test or self-test, whatever the test, you use the test kit to get the result, which is the measurement, D. So D is the data, right? The measurement. And C is the truth status, true condition. But so what we are really interested in is to understand, given the data, right? Given the data, what is your status, true status, right? So that is the base data. But this one is too simple, right? To be useful. So we maybe want to use this conditional base data. So this X has more information like age group, right? So X can be gender, age group, race, all this information, demographic information can be put in. Then maybe the prediction is much more accurate, right? So that is basically the value of this conditional base theorem. And from here to here, it's not difficult. We just put X to every right side, right? So X here, put X here, because X is given. So from here to here, we just put X everywhere on the right side. That's it. Okay. But that is good. But the problem is that this guy, it's not really easy to model. So we want to do some simplification. So that is this one. So assumption is that the assumption may be true or maybe not true, but sometimes we make it for the sake of the feasibility. So we assume, okay, that maybe my test result should depend on my true status, whether I'm in the COVID or not COVID. And my other demographic information is not really relevant. So, well, I'm not sure whether this is really true or not, but maybe not true, but still the effect on X is negligible, okay, compared to the effect of C, right? So the test result should definitely depends on my true status than my other characteristics, right? So maybe this is not terribly bad assumption. Okay. And actually, because whenever we have some important concept, it has a name. Because we want to, understand and make others understood, right? So the name that we use is a non-differentiable measurement error model assumption. Okay. What do you mean by non-differentiable? Non-differentiable means that you cannot really, so this X, so non-differentiable with respect to X. You cannot, so X doesn't really distinguish. That is the kind of meaning. And that actually gives a simplified Bayes result. Okay. And now the difference is that the X disappears in this part. And now I'm gonna, so from here, many interesting stories can be developed. Okay. So this is the left side here is what we want, right? What we really want is this one, to compute this conditional probability of the true status given my data and my other information. That's it. And then to construct this one, I want to use this Bayes theorem, but this Bayes theorem has two components. One is the model about P given C. The other one is the model about C given X. So we have two models. And because they are important, we also have a name. Okay. So the first component, P given C, is a model about your data, given the trace status. So we can call it data model. Okay? It's a model about data, so data model. And then C given X. C given X is called process model sometimes. So process model means before we observe the data, it's about true status. Okay, true status behind our observation. So that is the process model. I mean, sometimes they have different names, but this is one way to make the concept. And the data model is usually assumed to be known. We'll get back to this point soon. You may wonder why, but what is this? So think about the COVID example. What is D given C? C equal to 1 means COVID, right? C equals 0 is non-COVID. D equal 1 is a test positive. D equal 0 is test negative. So this number, this probability is actually the false positive, false negative probability, right? And that is usually known for the kit, for every kit, test kit. The company, company of the kit, test kit has their own analysis and give that information, right? I mean, you can check in from the website, whatever. This is, so you don't have to, you cannot really, estimate from the client. I mean, the consumers don't know, right? I mean, we cannot really have the resources to do all these experiments by ourselves, right? So this is pretty much given. But this one is something that we investigators are interested in So the process model is a model. So about the process as a process structure. So suppose we can make a parametric statistical model, right? Okay. And then the problem reduced to estimating setup. Okay. And so tricky part is that the true status is not observed. If we observe, right? If we had observed this, it's easy problem, right? If you observe if you observe C and X and try to estimate theta, no problem. We know that, how to do that. But problem is we don't observe C, but we do observe D. That is the so okay. To make the presentation simple, we'll assume that C is 0 and 1. So this is the basically the framework. So here you can think of it. This is the place we live, right? In the ground, we observe D, we observe X. This is like a heaven. Okay, we don't really observe. I mean, this is God. So this is the God's word, and this is a human's word, something like that. And so God may know, right? But we don't know. See, but we can still make some connection. So the relationship between C and D is a data model, right? The relation between X and C is the process model, right? So what we are interested in is to understand this one, actually, this one. Okay.
So how do you get either of those given that we don't know C? Like, how do you estimate or know either of those if you don't know C?
So yeah, so that is actually what I'm going to talk about.
Okay.
So don't worry.
Okay.
So yeah, that's a good question actually, right? How can we really estimate setup, right? When we don't observe C, but we have a proxy D, and we do have an understanding of the mechanism between the true C and proxy D, and use that how to estimate the setup. That is our fundamental problem that I'm going to explain very shortly. Okay.
So is it like X is the covariate and we are actually, the response is kind of D as it's in the cross. So X is like covariate some characteristics of something and D is the response. And is it something like that C is the hidden causal relationship between X and D?
Yeah, that is a good question. So actually, this is covariate, right? This is our kind of proxy outcome. So you could actually build a model on D on X directly, but that's not scientifically interesting. You are not really interested in that model. What you are interested in is this model. Because what we are really care about is what is the risk factor. For example, smoking, right? So smoking or pregnancy has an effect on the getting COVID, right? That is the real question that you are interested in, not the proxy measurement. So that's why we care about this model still, but because we don't observe this one, we need some proxy measure, and I want to do something. Yeah.
So we have information about D, right?
We have information about the mechanism.
Yeah, that's why we are making the relationship to get the relationship between C and D.
Right.
Wait, so how do we know the relationship between C and D?
Huh?
How do we know the relationship?
So that's next page.
Okay.
So that is a data model, right? So data model. So for example, in the COVID, test and COVID example, this is alpha basically characterized by alpha and beta, sensitivity and specificity, right? Parameter. So that may depends on different. So different measurement, we may have different alpha and beta, but we do know. So they are given. Okay. So we don't, okay, so alpha and beta is given, and we only care about theta. So that is the point. And processor model is something that, right? So this is we care about. So we are interested in, estimating theta, and sometimes we want to do test about theta, right? Some component of theta, because whether smoking or having exercise, right? Or you suppose you eat certain formula like zinc every day. Will that help getting lowering the probability of getting the COVID, right? This is really an important question we want to address. And so that is so basically your hypothesis should be built in to your model, and you want to, but the problem is that you don't measure, you cannot really measure C. Okay. So let me repeat. So if the parameters in the data model are assumed to be known, that may be strong assumption, and there may be some barrier into how to do that, but for the first day of the class, we just assume that it's known. Okay, we start from the simple setup and then move on to more typical setup later, rather than starting with the more typical setup first and then get everybody lost. That's not really what I want to do. So anyway, so that is the first message. And then if you true label, okay, C is just a label, right? So if true label is observed, then no problem, right? You can just do maximum likely estimation. And this is actually the log-likely function, okay, from the Bernoulli type logistic regression. So this is a logistic regression model, and this is your log-likely function, and you maximize. So this notation, let me just okay. So this is CLC theta is this guy, right? So you observe CI. So CI is a little bit tricky, but here, suppose we observe this. CI is observed, XI is observed. So you can compute everything up to theta, right? So up to theta. So this is basically a function of theta. And then you want to maximize over theta. And then suppose you are able to get the maximizer. That is the notation. The arg means the argument that maximize this function is called theta hat. Okay. So that is the maximum likely estimator. And you actually, this is, if you view this way, this is the machine learning, they are called classification problem, right? So you can actually, this is one particular loss function, and you can actually use a general loss function with different, softmax or whatever, lot of different ways of doing classification. So, but the point is that you once you have defined the loss function, you can put it to your optimization problem and solve the your estimator. That's it. If you observe CI, okay. So now I'm going to briefly talk about the learning. So 10 to about 10, 15 minutes, no problem. So I have enough time. So, okay. So this kind of problem can be named with learning with noisy labels, right? So what I mean by that, label means CI, right? Original label is accurate label is CI equal to 1, CI equal to 0. That is the accurate label. Noisy label is noisy version, which is DI. Okay. And learning means we want to estimate theta, right? So direct approach. Okay. Well, using the model, data model. So this is a data model, and this is process model. So data model and process model can be combined to get your marginal distribution, marginal probability of your data. Okay. And so you can actually know all this. You know this parameter beta and C equals, so C equals 0, right? C equals 0 is beta. C equals 1 is minus 1 minus beta. And this functional form is a logistic regression model, right? So you can, it's not really, pretty, but still, it's a closed form expression, right? As a function of zeta. And then that means you have a observation, an outcome variable, and covariate. And you have a model. So you can actually maximize it using the log likelihood, right? And using the log loss function and compute the MLE. So that is one way. That is, we can call it direct approach because we can directly derive your marginal probability of your data given the covariate, and then from that you can apply the observed likelihood, log likelihood directly.
Sir, I have a question.
Okay.
So here C is, we are assuming the C is observable here? Unobservable.
C is, so whatever is red means unobservable.
Um,
So we have two possibilities. So for D equal 1, right? For D equal 1, we have two possibilities with C. C equals 0 or C equal 1. So C equal 1, we have this. C equals 0, we have this. So that's one way. The tricky part, so conceptually makes sense. The problem is we have this is the simplest possible example, right? C is binary, C equals 0 and 1, D equals 0 and 1. So everything is very simple. But suppose C is continuous. Okay, it's continuous. Then this one will be integral. And it's a little bit messy, right? I mean, then how you actually derive the optimization with the integralized density function and probability, that's not fun. So usually, I mean, the concept is simple, but computationally, it's not really attractive. So direct approach. That's just the direct approach conceptually. And secondly, EML. So this is, recall that this is overcorrection. Overcorrection means I'm going to go over the high level first before I tell you the details. So I didn't even want the EM algorithm. So it's like a preview. If you watch the movie, right? I mean, you have a preview, and preview gives you some slots. I mean, show some best shots of the main movie. So that's basically what I'm going to do. So this is essentially preview. So I don't expect you to understand everything here in the first day, but we will go. So EM algorithm is one of the core tools that we are going to study in very details. So maybe third week we'll fully at third week we'll probably have a lot of opportunity to study this EM. So don't worry for now. But let me nonetheless let me just explain the concepts. And if you cannot really follow, that's fine. So the idea is first define the logarithmic function using the true label CN. So this is the logarithmic function you would use if you had observed the CI. But in practice, we don't observe CI, so we cannot really compute it. We cannot really input CI here because you don't observe CI. what you observe is DI. So the idea is, okay, why don't you compute the conditional expectation of this log likelihood given your data? But when you compute the conditional expectation, this expectation is evaluated at certain parameter value, which is so current parameter. So computing the conditional expectation is E step, but when you compute the conditional expectation, you need to know the current parameter value. So that is theta t. So once you use this E step, end of the day, you obtain the predictor, best predictor of your CI, unobserved CI, using the current information. Okay, and so this one is computable as long as you have a parameter, current parameter value. So this one is computable, so you can actually put it into your program, okay, as an input. But this you can treat it as a outcome data. So you can treat it as a CI, choose CI, unobserved CI, and put it and to maximize. So maximize is this one is M step. So M step, you basically have a updated parameter value. Okay. And so since you have updated parameter value, you can actually improve your estimation. So that's why you get an iteration. Okay. But that is probably too much for the first day of the class. Okay. Yeah. So there are some details, but that's basically the main key core or one of the core contents of this course. So usually when you apply the E step, you will need to use the Bayes theorem. So you can see that the same Bayes theorem that I covered in the very beginning, it appears now. And then so to implement M step, notice that the M&A procedure is a mapping. So this is actually mapping, right? I mean, you put it your input data, and this is your subroutine, and then you compute, you update your plan. So now, since you don't observe a CI, you basically use the CI head as an input, and then update your plan. So that is basically the way of you compute the M step. Okay, I don't know whether this one really helps. I'm not sure, but this is you don't know. Okay, you don't observe. So if you observe it, everything is easy, but you don't observe it. So to compute it, you use parameter, and then once you obtain this one, you have some information about CI, then you can actually improve your estimate. So improving your estimate, parameter estimation is an M step. Improving your missing data prediction is an E step. So the whole idea is to end of the day, once you obtain the parameter, iteration, since you do iteration, after all the iteration, you end of the day, you will convert, it will converge. If it converges, then you can use it as the final estimator and compute the conditional expectation. So that means given your current data, right, the test data and cover it, you can actually obtain the best prediction of the missing data, CI. And in the classification, it is sometimes called the denoising label. You have a label, okay? You don't know the true label, but you do have a noised version of the label, right? Noised label, and so you know that it has noise, so you want to denoise it, some sense, right? So this is the best you can do, given the parameter, and then. So in statistics, we call it prediction problem. latent variable prediction. So CI is a random variable, and but a random variable is missing. So then we want to predict it. But to predict it, we need to compute the parameter first and evaluate it under the current parameter value. And usually Bayes' theorem plays the key role in obtaining the prediction model. So that is the basic idea. And then in statistics, we care about uncertainty, quantification, and things like that. So there's some details of how you actually quantify your prediction error. So that your final prediction has a estimated parameter. So you can see that if your conditional expectation has an unknown parameter. So your error has a two part. One is the genuine error. The other one is the error due to estimating the unknown parameter. So the first part is the genuine prediction error. So that is, you cannot really avoid this part, no matter how many sample sizes you have. Even if your sample size goes to infinity, this one still appears because you don't observe CI, true CI. You only observe DI, right? So then you cannot really avoid this part. But you can avoid this one because if your sample size goes to infinity, then this one will converge to this, right? True parameter. So this one will be small. But anyway, we have these two components. So these variables and these variables. And so that is basically the prediction error decomposition. So this is the last page. So here's the summary. So many statistical problem has this kind of structure. So you need to first make a model assumption, model specification, but in the model, there may be some latent missing variable, latent variable. And that latent variable really help you to give interpretation. And so you can basically model specify the model and define what is the missing variable and how this missing variable plays the role in capturing the structure of your data, right? And then so this model specification is actually give you some framework. You have a frame. Basically, you have a glass. You now have a statistical, camera. You have a statistical view, right? Lens to interpret it as a statistical problem. So then this is actually a statistical tool, right? Once you frame your real problem into a statistical problem, then there's a tool which I plan to cover in the course. So this is the examples of the tools that we covered. And then once so the tools actually has a parameter estimation component and prediction component, usually, right? And then and also as a statistician, we probably want to quantify the uncertainty in the so this is the basic summary of the statistical steps for your problem. So this is the overview lecture I give today is under the framework of the measurement error model, right? But if you think about random effect model, mixture model, right? They have different way of framing. They are totally different class of models, but the structure are the same. So that is very actually interesting part of this lecture because it gives a unified way of doing many complex problems into the missing data framework. Okay. Well, thank you. I think that's all for today. And oh, sorry, I missed that too. Okay.
So will it be more like theory or coding or what kind of?
Yeah, currently it's a little bit more like an example and theory solve it, but I hope I can give you some coding too
Okay, later on,
later.
okay.